Today, we're going to talk about stars and constellations. Now, did we? No, we didn't. We didn't talk. I mentioned it a little bit in our keynote videos, but I'm going to review somewhat today. So, space is a vacuum. That's what we're going to be talking about probably till the end of the year. We're going to be talking about space. Now, space is vast. It is huge. So it's hard for our human brains to understand how big space is. You really have to be someone like God to understand just how big it is. So when we're talking about these things, if you don't fully you're like, my brain can't wrap around that, don't worry about it. Neither can mine. But we got to understand that space is very different from here on Earth. For example, space is a vacuum. Not like a vacuum like your mom or dad or you used to clean. When I say vacuum in space, does anybody know what that means off the top of their head? A vacuum of space. Okay. Yeah, Cash, do you know what it means?
A vacuum of space means that things are just infinitely sucked in to it.
Kind of. Yeah, we get that idea of being sucked in, but it's a little bit different than that. If you're inside of a space station, you can get sucked out. Kingston, what's a vacuum of space?
It is nothing.
Yeah.
It is literally no stars, no life, no matter, no planets, nothing.
Yeah. So the key word that he said is matter. Now, everything that you see, and even things that you don't see, are made up of matter. Your computer, your iPad, your hoodie, the coffee or tea that's in your cup, the air between you, all of it is matter. It's what stuff is made up of. Everything has mass. Even the tiniest atom in a helium molecule is made up of something, and we call that matter. Everybody with me so far? Space has no matter. There's no air. There is dust and stuff floating around in space, but in the distances between us, there's nothing. So when you and I were all in a classroom, even though it looked like there was nothing between us, there is something. There's something between my computer screen and me. What's between my computer screen and me right now? Kezia? Air, exactly, right? And so I can make it do stuff. I'm making it make sounds as I clap my hands together, pushing the air out of my way, right? But in space, there is no air. There's nothing. And so it's called a vacuum. In fact, if the Star Wars movies were actually realistic, all of the cool space battles with TIE fighters and stuff would be silent. Why would they be silent? Lucy, I think you have your hands up. Oh, there you go. Go ahead, Lucy.
Because they have no air, so there's no noise.
Yeah, they'd have no air, so that there would be no sound that's what sound is. The air is sound waves passing, vibrating off of air particles. But that would be a boring movie if all of the Death Star and everything was just silent. Also, there would be no fiery explosions. There'd be a second as the fire lit up, but there can't be any fire in space. Why? Kingston?
No oxygen.
There's no
Fire
oxygen.
needs to feed off of oxygen.
Fire needs oxygen, and there is no oxygen. So, because there is no matter, that makes space dangerous, but it makes it also unique. Let's say that Xavier throws a baseball. It is not going to fly forever, whether it's Xavier or it is Clayton Kershaw or anybody. You could launch a baseball out of a cannon, and sooner or later, it is going to come to a stop. Why? Why will a baseball not fly forever? Kezia? I think you got it right, but you're breaking up on my computer. Lucy?
Because of gravity.
Gravity is pulling it down, and the air molecules are hitting it. Have any of you guys ever been in your parents' car and you roll down the window and you do this thing with your hand? So the air, and then when you do it like this, it makes your hand push back, and so you can kind of do that. So the air, as you throw a baseball or something, the air particles are hitting it, and gravity is dragging it down. Then when it lands on the ground, the grass and the friction are causing it to stop. A object in motion will remain in motion unless acted on by an outside force, gravity, air molecules, whatever. But in space, there are none of those things. There is gravity, but if you're outside of its reach, so if Xavier was in the International Space Station and he was floating outside and he threw a baseball, that baseball would continue going the direction that he threw it from now until Jesus returns, unless it bumps into the sun or something, because there's nothing on it to act outside of it. So a vacuum means that there is the absence of matter. This is going to be on your test later. Also, so space is a vacuum. Space also has extreme temperatures. During the day, it is hotter than it is at night. When the Earth turns away, last night when we were all sleeping, our side of the Earth was facing away from the sun. But we did not freeze to death. It got a little colder, went from like 75 degrees to something like 40 degrees, but it did not freeze over. Does anybody know, I don't know if you guys have learned this in other classes, why we do not freeze to death every time we turn away from the sun? Kingston?
There are other stars?
That's a good guess. No, they're too far away. I'll say it like this. If Lucy was floating, let's say that the sun is this picture of Aiden, and I'm the space station. If Lucy was on this side of the space station, away from the sun, in the sun's shadow, it would be something like below 200 degrees Fahrenheit. If she was on this side of the space station, directly in front of the sun, it would be something like 370 degrees Fahrenheit. So it's burning hot on this side of my head station and freezing cold on this side, because there are extreme temperatures in space. However, here on Earth, we have an atmosphere, and that atmosphere is a blanket of air that surrounds us, and it traps in the air like a blanket. We call this effect the greenhouse effect. Raise your hand if you've ever heard of the greenhouse effect. So as the sun's heat energy hits the Earth, some of it hits and bounces back out, but some of it gets trapped, and it's just like a blanket. When you're cold and you put on a blanket, you get warm. Does anybody know how a blanket works? Why do you get, when you put on a blanket, you just feel snugly warm? Why does a blanket make you warm? Why does a jacket make you warm? Anybody know? Aaron?
Because it lets in all of it basically keeps away the cold air, and
That's a good guess.
and
Sometimes
also some things keep in the warm air.
you're almost completely right. It blocks some wind and rain, but mostly it traps something. And what is that? Kingston? Sorry, I'm trying to see everybody's. Go ahead, Kingston.
It's your body heat. It's trapping your body heat inside.
Exactly. All of us are 98 degrees inside. Have you ever seen, like, if you've been running around outside and you see your breath and you see kind of like steam coming off of you? That's because inside we're 98 degrees Fahrenheit. when you put on a sweater or when you put on a blanket, that heat that's coming off of you is trapped inside, so it keeps you warm, right? So inside the earth, the atmosphere acts like a blanket and it traps that heat inside. So even when we turn away from the planet, from the sun, instead of freezing to death, we have that trapped heat from the day. Did that make sense? But in space, since it's a vacuum and there is no air, you can't trap heat. So when an astronaut goes into space, he or she needs to be in very protected environments. When we go to the moon, it's the same thing. We have to have protected environments, because if we didn't, if Noah found himself outside of a space station with no spacesuit, what would happen to Noah with no spacesuit on? Cash?
First thing, he would have no oxygen,
Right, so he'd suffocate. Sorry, Noah.
and he would probably either freeze to death or burn to death.
Freeze or
depending on
burn
which
up.
side he's on.
Yeah, because it's freezing cold or super hot.
And I think crush him. I think something like that.
You're close. Does that, Lucy, do you know what the last thing was? He would either freeze, probably freeze, and he would suffocate. But what's the last thing that would happen?
He would feel so much pressure. Like I can't remember it, but it's something about pressure.
Yep,
How it
you're
would,
exactly right.
Yeah.
Have any of you guys ever gone camping in the mountains and you like take up a bag of chips and here it just looks like a regular bag? Like when we were supposed to go to Astro Camp, when we get up to Astro Camp, everybody's supposed to bring a lunch. And when we get up there, all of the chips bags are all super puffy because down here at ocean level, we have more air pressure. And when you go up high in a mountain, the air pressure is less, and so things start to expand, right? So if there's no air pressure at all outside, everything inside, all of the pressure inside would expand, which would make you explode. Not like burst like a melon, but all of your blood vessels and everything. So it's extremely dangerous. You cannot just play around in space. If we ever go to the moon, don't mess around in space. All right, so that is roughly the nature of space. Extremes of temperature and a vacuum, no matter, no particles, nothing. We're going to be talking about stars and galaxies in this chapter. Stars are the main building blocks of the universe, and stars are extremely hot, extremely large, burning balls of gas. Raise your hand if you've ever seen the movie Lion King. And you know when they're all like looking up into the stars and Simba is like, what do you think is up there? And Timon's like, well, they're fireflies that got stuck. And then Pumbaa's like, they're huge burning balls of gas millions of miles away. Pumbaa's right. Because they are massive. And if you went into the innermost core of the sun, you would see particles, atoms of helium and hydrogen hitting each other. And they hit each other going so fast that they fuse together. And when they fuse, they let off huge amounts of energy. It is the same process as when a nuclear bomb goes off. So a nuclear bomb, when it is dropped, it is set to take two atoms. Aaron, you're killing me. The two atoms hit each other and they fuse and they let off enough energy to destroy a city. If a nuclear bomb landed on Los Angeles, that would be it for all of us. And that's just two atoms. So you can think of a star as like thousands of atom bombs exploding at once. Boom! But because it's so big, gravity holds it together. So it's all of these nuclear explosions happening, but being held together. And it's been happening for millions of years, and it will continue happening for a very, very long time. So stars are gas particles that are hitting each other and exploding. Does everybody get that kind of? So, galaxies are made up of billions of stars. Now we're going to have our first kind of head-breaking moment. If you wanted to count to 1 million, you would get bored and stop. But if you wanted to count to 1 million, it would take you a long time. If you wanted to count to 1 billion, it would take you years. I'm talking if all you did all day was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, for forever. A billion is a very difficult number to understand. And there are billions of stars in each galaxy, Cash. And there are billions of galaxies in the universe. In fact, there are so many stars that if you went to a beach and counted every individual grain of sand, and you counted all those up on the beach, then you went to every beach on the entire planet and you counted every single grain of sand, there are more stars than there are grains of sand on this planet. There are almost infinite. That's just in the observable universe, the part of the universe we can see with our telescopes and things. There are more stars than grains of sand on the planet. So we could, if we were in class together, we would talk about, maybe why did God create that? And if there are almost infinite number of stars and many of those stars have planets, does another one of those planets have life forms, right? Then we'd talk about aliens and we would have kind of an interesting conversation. Now, because we only have 30 minutes, we're not going to talk about that. But we need to know that those stars, when you look up at the night sky, all of those stars that you can see, those are not all the stars. And even those stars are more than we can count. Now, we live in LA, so we can't see a whole lot. But if you were out if you've been camping, you see all the stars, you understand how much those are. So galaxies are groups of stars. Everybody with me so far? Now, before we go any further, we need to talk about nebula. If you have your book out and you turn to page 185, you will see pictures of nebula, Nebulae. Cash, will you turn off your camera if the dog's gonna, I get it. A nebula is an extremely large cloud of gas and dust. And nebula are how stars are made. Because all stars are made through gravity. Every single thing that has mass has gravity. So, does Kezia have gravity? Kezia, do you have gravity? Yes, you do. Does Mr. Frazier have gravity? Noah, do I have gravity? Yeah, I do. Does my super awesome veggie smoothie have gravity? Lucy?
Yes.
Yes, it does. So even air particles, a single air particle on the tip of my finger, and there are, could be hundreds of them, has mass and therefore has gravity. So a nebula is filled with gas and dust, all of the ingredients for stars and planets. So before God created this solar system, it was just gas and dust. Then this is how I interpret it, and scientists. And the gas and dust have gravity, so they start pulling things to themselves, right? If there was nothing else in the solar system and it was just me on one side and Jude on the other side, over the course of billions of years, we would come together because everything has gravity and gravity attracts. So the gas and the dust start coming together and hitting each other and making bigger balls of gas and dust. And the bigger they get, the more gravity they have, so the more they pull together. And they become even bigger, which gives them more gravity, which means they pull more things together. Does everybody understand? So it's this chain reaction until there is enough gas to where the gas particles hit each other and fusion happens. And when the fusion happens, what happens when atoms fuse together? Anybody remember? Cash, what happens when atoms fuse together?
They they become, what's it called? Oh, they explode. They explode.
Exactly, they explode like an atomic bomb. And so a star will kick off when enough gases come together and it explodes and a star is born. And when that star is born, it blows the rest of the gas and dust away. Now, what flies farther away, do you think, the gas or the dust? When a star is born and it starts whoosh, do you think the gas is going to fly farther or the dust is going to fly farther? Kingston?
The gas.
The gas, right? So the dust will fly and the dust will start to form together and make rocks. And then the rocks will form together and make boulders, and right? And so you have the rocky planets, Mercury, Venus, Earth, and Mars, are close to the star. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are further away. And so this is how God created every star and planet in the universe, according to scientists. So a nebula is the cloud of gas and dust from which all stars and planets are made. Okay, so how do we classify galaxies? There are 3 types of galaxies that we are going to talk about in our book. There are the spiral galaxies. If you have your book, you can turn to page 183, and you'll see how spiral galaxies kind of look like a spiral, right? And they have arms kind of sticking out. Now, that picture on 183 is a picture of the Milky Way galaxy. Now, it can't actually be a picture of the Milky Way galaxy. Why? Lucy?
Because it's.
Did you have your hands up?
Probably,
I couldn't tell if you had your hands up because your Did you have your hand up?
yeah. No,
Okay.
I didn't have.
All right, sorry. Kezia, do you know why that couldn't be a picture of the Milky Way galaxy? Why? Sorry, Kezia, I can't hear your audio. I'm sorry. This is annoying. Why can it not be a picture of the Milky Way galaxy? I would ask Maya, but she's concentrating on something. Kingston?
Because we don't know all of our own galaxy, all of the Milky Way galaxy, so it's impossible for us to write all of it down in the book.
Well, yeah. And nobody has ever been that far away, right? You can't take a picture of Earth unless you leave Earth, right? So in order for us to take a picture of the Milky Way galaxy, we would have to leave the galaxy, which, at least at this point, is impossible. So one last little thought experiment. We're almost done. You guys have been very patient. I appreciate it. Does anybody know what the fastest thing in the universe is? Don't say the Flash. What's the fastest thing in the universe? Lucy, this time I see your hand up. What is it?
Light?
Light is
Isn't it like the speed of light?
the speed of light is the fastest thing. And light moves so fast that it can travel. It's 186,000 miles per second. So that means in 1/1000. In that amount of time, light can travel around the Earth 12 times. That's how fast it is. If you were traveling at the speed of light for a year, now this is so fast that Einstein says it's impossible. Like if you were traveling that fast, that your body would like morph into a different shape. But let's say you could travel the speed of light. It would take you a year and a half to get to the nearest star to the sun, which is Proxima Centauri. So that means that if you could travel the speed of light to get to the very next star, you guys would be almost graduating from 8th grade by the time you got there. If you're traveling at the speed of light and you wanted to go from the sun to the middle of the galaxy, it would take you, I think, 10,000 years. And if you wanted to leave the Milky Way galaxy at all, it would take you, see, look at the bottom of your page that it has a little thing. So 25,000 light years to get from the sun to the middle of the galaxy. So if you wanted to get to the other side, it would take you something like 60,000 years traveling the speed of light. That's just in our galaxy. So trying to get out to another galaxy, you're joking. So space is big. I've made that point. So you have the spiral galaxy, which Milky Way is one of. We have a elliptical galaxy. Elliptical means like an oval. An ellipse is kind of like an oval. So spiral, elliptical. Then we have the barred spiral, which is kind of a variation. And then the last one is an irregular galaxy. Now, irregular galaxies do not have a shape. Most galaxies have kind of a spinning shape because everything orbits because of gravity, like our solar system. But some galaxies are so old that they have kind of just fallen apart and they just look like blobs. So the three main types are spiral galaxy, elliptical galaxy, and irregular galaxy. You will also have, for your test, you'll need to know the barred spiral. But so, in summation, galaxies are made up of billions of stars. The universe is made up of billions of galaxies. Each star is made up of gas, and all stars are born from huge clouds of gas and dust called nebula. Any last questions before I let you go back to Miss Helenice? All right. Yeah, Kingston. 1 second, sorry. Unmute. Go ahead.
So, if all of space is, most of space is a vacuum, then, and we can't travel outside of it, and then how would we ever be able to see other planets or visit other planets if it would take that long to get out of the Milky Way?
You mean other galaxies?
Yeah, other
galaxies.
galaxies.
That's not happening. I mean, unless like the humans create how to like go through wormholes. But even traveling at the speed of light, it would take you a year and a half to get to the next place. And if you wanted to get to, let's say I found life and it's, at X star. Well, that star is 200 light years away. Well, how do you get a human who doesn't live that long, even if you could travel the speed of light? Does that make sense? So you could, I guess, cryogenically freeze the human and then shoot it over traveling the speed of light if you had all this technology. Then when it gets there, unfreeze it. Does that make sense? But
yeah,
we don't know how to do either of those things. But then also, let's say Kezia goes to this new planet. Well, she will have been frozen for the last 200 years. So when she wakes up, it'll be the year 2220. But space travel is hard. If we wanted to go to Mars, and there are people who are planning right now to go to Mars, it's going to take us something like 9 months just to get there. And that's traveling at the speed of a bullet. So if you could manage to do that, so that means that, like, let's say that Lucy wanted to be an astronaut and she did all the training and she did everything and she's like, okay, I'm going to Mars. Then they make a safe, launch. They get out to space. Then she wouldn't even get there until 2021. And then she stays there for however long. And when she gets back, so by the time she got back, it would be like, years of her life. Does that make sense? So who knows? But space travel is fascinating. Space is very interesting to me. So in the future, anytime we have time, I'd like to have these discussions because I like thinking, time travel is possible. If you can travel at the speed of light, time travel is possible. And when we meet on Friday, if you remember to ask me, I'll explain how you can travel in time scientifically. Not like if you have a DeLorean and you go 80 miles per hour, then you go back to the future and have crazy hijinks. But you can do it. right, guys. Have a great day. I'll see you on Friday.
We're supposed to go to Miss Alanis, right?
Correct.
Okay.
Bye, Kezia. Bye, Kingston. Hey, Dawit. Haley was here 5 minutes early, Dawit, and I didn't admit her because I was still talking to 6th grade, and she bounced. One second, I'm gonna unmute you. My bad, dude. What did you say?
I thought I said that's kind of sad.
Enoch and Savad are here.
Savada's not here for some reason. I don't know why. And Enoch said he was about to join, but I don't know if he can find the parent letter or whatever where it has the meeting ID.
Enoch's here.
Oh, here.
Haley's here. We're gonna try and do a little bit of science and history.
Okay.
You know, this is kind of not fair to all of, well, I mean, I don't know how much kids care, but there's no way that you can teach the amount of material that we're supposed to in online classes. Did you know? What's that?
I was gonna say, I wish that we had like at least an hour with you.
Yeah, man. I, you know, it's funny. I don't want to sound mean, but I don't enjoy teaching 3rd grade as much as I enjoy teaching middle school. You know, they're sweethearts and they're always like super well behaved, but how much can you teach in an 8-year-old, a 9-year-old? You know, you really have to kind of break it up into baby pieces, but you know, that's just kind of how, unless we made the class, unless we did this from like 9 till 2, and nobody wants to do that. But we're going to jump ahead. Turn in your science books really quickly to page 299. We're just going to talk for a second about this, and then we're going to go back to history. I'll be right back.
Okay. You know, why don't you have a camera? Huh? I can't hear you, Haley. Omich? Oh, open mic. I know you can't unmute yourself. Only Mr. Fraser can do that. Yeah, I know. It's kind of tough. I know. I mean, well, at least you have a mic, right? I mean, no, a picture. Oh, what page? Sorry. 299.
All right, sorry about that. Side note, I was thinking about you guys and thinking about, I remembered a basketball drill that I used to do, because I was like, how are they going to practice basketball? They can't leave the house. Well, if you can shoot in your backyard and everything. But we used to do this thing to work on ball handling skills, where you would sit down like this, and then you would get a ball and you would dribble it. Because you know how you have to, like, you're supposed to dribble with your fingers and like the front of your hand, not your palm. Yeah. And you dribble it like this, right? And then you dribble between your legs like this, right? So dribble with your left, boom, 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 then dribble, boom, 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 dribble, boom, 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 dribble. And then if you got good, then you could dribble, and then you bring your foot back and dribble between like this. And then you move your foot back and then like this. That was something that I used to work on. You could do that sitting anywhere. And it kind of looks cool once you can learn how to do it. Right.
I used to do that, but I didn't know that it actually helps with your ball handling. I thought it was just something people did because they were just bored.
it does not help as much as like dribbling at a full run, right? Like,
Oh,
you
yeah.
know, if you really want to do it. But the thing about handling a basketball is getting your hands used to the movements. You know, when most people dribble, what do? They look at the ball, right? Because they don't want to dribble it off their hands. But people in the NBA don't look at the ball, and that's because they have dribbled that dang ball so many times that they just instinctively know where it is. They can feel it in their hands. And so even like dribbling, if you can dribble with your head up and you know exactly, and you can always keep it under control, that's ball control. Anyway. All right. So anyways, we're going to talk a little bit about science. We have finished our discussion of fish. We're talking about